Hello, in this video we're going to talk about the practice test leading up to test number 4 this week in college algebra. And there are a few questions on this practice test and also the actual test that we may not have explicitly covered in this most recent unit, but it is content, it's material that I feel you should be familiar with and or confident with. And so we'll just start off with a question like that right now. We have 3 functions given to us in question number 1, and we need to determine the domain and range of each based on the graphs below. So we have talked about domain and a little bit about range this unit in terms of the functions that are identified and given to us, but not based on the graph. But I think we can handle this. The domain, of course, is representing all x values appropriate or that are associated with a particular graph or function, and the range, of course, are all y values associated with a graph or an equation. So look, if I look at question part A, the x values that are associated with this graph, it looks like they start here at 5 and they transition to the left. This arrow, of course, indicates that the graph is going to continue leftward without stopping. And so I would say something like this. The domain of this function would be all x values that are less than or equal to 5. We could also use our interval notation and say that x must be an element of the numbers from -infinity up to 5 inclusive. We're going to say 5 is inclusive because if I start considering any of these x values along the way, all of these x values will produce a coordinate on the graph, including the x value of 5, because there is precisely a coordinate right here. So we do want to include 5, whether we show the inequality or the interval notation. As far as our range goes, well, now we're talking about the y values and what y values are associated with this graph. Well, again, it looks to me like the y values start at 0 and then they increase upward. Any y value that's bigger than or equal to 0 will be represented inside this graph. So we could say something like this, that our range are all y values that are greater than or equal to 0. Or in other words, we might say that the y values must be an element of the interval of numbers from 0 to infinity. So why don't you try part B on your own and C as well. Pause the video now and resume playback in a moment to check your work. In part B, it looks like all x values are represented along this real number line, so we could say that all real numbers are appropriate domain for this function. If we're using interval notation, we would say something like this, that the x values exist between -infinity and +infinity. For our range, it does look like the function reaches -2 and +2 and every number in between. So we'll go with the y values in between -2 and +2 with the inequality notation. And as intervals go, we'll use -2 to 2 using the square brackets. For this graph, we should recognize it as an inverse squared graph that's been translated up 1 unit. It looks like all x values are in use in this particular function, but based on this additional note, we're told that the graph approaches but never touches the y-axis or this dashed line. So if it never touches the y-axis, that's when x is equal to 0. So we would say the domain are all x values where x is not equal to 0. Or if we use interval notation, we would say that x is an element of the list from -infinity up to 0, but not including 0, joined with the list of numbers from 0 up to infinity, not including 0. So clearly it's a little bit easier to write it using this modified set notation, and that would be just fine. We talk about this in terms of a domain restriction. For our range, we're talking about the y values, or I should say the y values that are represented by this graph. Both sections of it are all y values that are greater than 1, but not including 1, not equal to 1. We're approaching this dotted line, but never going to touch that dotted line. And with our interval notation, we would then say that y must be an element of the group from 1 to infinity, where 1 is not included within that interval. So in the next collection of problems, it says to classify the functions as even, odd, or neither, and explain your answers. I don't particularly like the way that instruction reads, so I think I'm going to change that. So we're going to identify or classify the functions as even, odd, or neither, and I'll say something like this, using algebra. And so that'll imply that you're using the algebraic method to establish whether these functions are even, odd, or neither, and no additional explanation would be necessary. I don't have enough room to complete all of this, so I'll just choose one of these examples. I'll go with part B, and you can use this same approach to test the others. So if I verify whether B is even, odd, or neither, the first thing I must do is evaluate the function at a negative or opposite of x. So that turns into 15 times negative x cubed divided by negative x to the 5th power plus negative x. The negative x value, when cubed, will also produce a negative result. So a negative 1 cubed is still negative 1, and x cubed is just x cubed. So 15 times negative 1 x cubed is negative 15 x cubed. And in the denominator, we see something similar happening. We have negative x to the 5th minus x. And what I'd like to show here is that in the denominator we have a common factor of negative 1. So with the numerator, negative 15 x cubed over the denominator, negative x to the 5th plus x. What this does for me is it essentially gives me a negative 1 in the numerator that can cancel or factor with the negative 1 in the denominator. Or more generally speaking, we see that the two negative signs cancel. And what I'm now left with is f evaluated at negative x, I should have really carried that down all the way here, f evaluated at negative x is equal to 15x cubed over x to the 5th plus x. And as it turns out, this expression here is exactly the same as what we started with, so therefore it is f of x. And we've just now shown that f evaluated at negative x is equal to the original function f of x. Therefore, by definition, we're dealing with an even function. You should recall that if you do not establish an even function after this first step, you would test for odd. And the way we verify an odd function, we wouldn't go through this, but the way we would verify an odd function is by factoring out a negative 1 from this expression. Now keep in mind that you don't factor a negative 1 from both the numerator and the denominator. Instead, you factor from either the numerator or the denominator. If you factor from both, that would be essentially factoring by a positive 1. So we could indicate that this is a negative 1 times negative 15x cubed over x to the 5th plus x. And we would only do so in the hopes of showing that the original function that we had rewritten would be equal to the original function that we were given with a negative 1 multiplying it. And we don't have that in this case. We don't have a negative 1 times the original function, so we cannot say that this is odd. But again, if we did not find an even function to begin with, we would test for odd. That was not necessary here. If we did have to test for odd, that's the process that I would go through. And of course, if a function is neither even nor odd, then we would say that it is neither. In question 3, we're being asked to decompose the functions into two functions so that y is equal to f composed with g. And I should indicate that we are interested in non-trivial solutions. So I don't want you to say that f is equal to x and g of x is equal to the composed function. So we want non-trivial solutions only. So here again, I'm not going to complete all of these, but I'll choose one to complete. And maybe I'll make it C this time. If I would like to compose this to an outer function and an inner function, of course f is my outer, g is my inner. I might say that the outer function in this case is equal to the natural log of x, and the inner function is 4 minus x squared, and that would be just fine. Another acceptable answer might be this. The f of x is equal to the natural log of 4 minus x, and my inner function is x squared. And so if I were to substitute x squared in place of the argument x here, I would still end up with natural log of 4 minus x squared. If I were to substitute 4 minus x squared into here, then I would still end up with the natural log of 4 minus x squared. Both of these results are acceptable as both are not trivial solutions. With number 4, we're given a collection of functions, f of x, g of x, and h of x, and we need to find the formulas and the domains or domain restrictions for the composition functions as follows. Here again, I'm not going to complete all 4 of these, but I'll choose one to complete as an example, and you can use that process to model what you would do for the other 3. So in this example, I think B looks kind of interesting to me. So we'll compose G with H. Now, if G is composed with H, where G is on the exterior, then G composed with H, which also may look like this with this notation. Let me make that a little bit more obvious. G composed with H at x would be the square root of something. So G is our outer function, and the something on the interior would be 2 over x. Now, as we've mentioned in the past, there are 4 steps to identifying the domain or the domain restrictions for a composite function. First thing we need to do is identify the domain or the domain restriction for the inner function. Now, my inner function was 2 over x. And with an expression 2 over x, all that we're worried about is x equaling 0. So we want to say that x is not allowed to equal 0. For step 2, we find the domain or the restriction of the domain for the outer function, which was this guy here. So we don't want x to be 0 for the inner function, and on the outer function, x could be 0. There's no problem with that. However, we don't want numbers that are less than 0. So what I might do is I might say something like this. Instead of saying x is not allowed to be less than 0, that's a bit of an awkward way to write this. I'm going to say that the domain for the outer function is that x must be greater than or equal to 0. We may only input positive numbers or 0 into a square root expression. Now for step 3, we take that inner function, 2 over x in this case, and set it equal to, or we use the restrictions or the domain for the step number 2, the domain from the outer function. We've got to find when will 2 over x be greater than or equal to 0. And in this case, there's not really any math that we would do to answer this, but if you just think about it carefully, then I think you can establish an appropriate result here. When will 2 divided by x be a positive number or equal to 0? Well, it'll never equal 0 because this is one of those inverse functions that never equals 0. In fact, I can't take 2 and divide it by anything to equal 0. But it will always be negative if one of these numbers, when divided, is negative. This numerator is always going to be 2, so the denominator takes on different values, as the variable indicates. And as long as this variable is positive, then 2 divided by that x will also be positive. So we're going to say that x must be greater than 0. Only positive x values make a result that's greater than or equal to 0. So in part 4, we combine our domains for part 3 and part 1. So when is x greater than 0 and when is x not equal to 0 simultaneously? Well, these two don't really overlap one another, so it's not like these two can exist simultaneously. Well, I guess they do overlap, but these two don't actually share any values. The only time that x is positive and not equal to 0 is if x is greater than 0. That would be the domain for this guy here, G composed with F. g composed with h. We can only use the function g composed with h. We can only use this function here if x ends up being a positive number. Now, for question number 5, two graphs are shown, and they're shown separately, not on top of one another. I think Math Excel had these two pictures superimposed, and that made it a little bit challenging for us to interpret, but I think we can work through them this way instead. Two graphs, f and g, are shown. Show your process, not just the final answer. So we're going to answer g composed with f at 3, and we need to show the process, not just the final answer. So if you want to show me arrows on the charts, that would be fine. If you want to show me some sort of algebraic expression, that would be good too. Here's what I would probably do. I know that g of f of 3 requires us to evaluate f of 3, so I'm going to go to the f function and the value 3 on the x-axis. So as I look up from 3, I see that the result is 2. I know that g composed with f at 3 would be the same as g of 2, therefore. Now I can evaluate g at 2, so I'll go to 2 on the x-axis and look up and find that g at 2 ended up being 4. So therefore, if g at 2 is 4, then g of f of 3 is also 4. For the second example, this is a little bit different. We're not evaluating f of g at 0. We want to know what it takes to evaluate f of g to equal 0. So in a sense, we need to know f of what number lands us at 0, because after we evaluate f, after g is evaluated, after we evaluate f, we end up at 0 to finish this expression. So what number acts as an input to produce 0 as a result in the f function? Well, that ends up being 6. So f evaluated at 6 would equal 0. And since we're working backwards, now we need to find g of what number produced 6. Well, if I'm looking for 6 as a result, here it ended up being the number 3 to make that happen. X was equal to 3. And so there's our answer. When solving a question like this, we're looking for x. When solving a question like this, we're looking for y, the result at the end. Now, by the way, we should be able to test or check our answer. Does f composed with g at 3 equal 0? Well, let's see. G at 3 equals 6. F at 6 equals 0. And that's what we're looking for. F composed with g at 3 does end up equaling 0. So I don't really anticipate any concerns or questions with part A. That's pretty straightforward. It's part B that makes people think, and you've got to pause and really think about the results there. But again, if you approach it in an appropriate fashion, I think you'll end up with the correct answer without too much effort. Now this question says that there's a graph, f of x, and it's shown in this first figure. So here's what f of x looks like. On the remaining axes, sketch the graphs of the following functions. So all of these transformations must be executed. We don't know what f itself is, but we should be able to complete the transformations based on our notes from this unit. So I'll complete a couple of these, but not all of them. Let's talk about A real quick. Since we have a subtraction of 2 on the outside of our grouping symbol, I know that when we add or subtract, that's a translation or a slide, and I also know when that translation is performed on the outside, then that's a vertical movement. So this is telling me, this minus 2, is that I'm going to take the original function and shift it down 2 units. If I were to put a 2 on the interior, I understand that this is a stretch. Okay, when we multiply, we stretch the graph, and since it's on the interior, that means it's a horizontal stretch, and also because it's on the interior, it performs the opposite of what we would expect. So there's no shifting or translating. It's just a matter of stretching, or in this case, compressing, because instead of being twice as wide, it ends up being half as wide. Horizontal movement because it's on the interior of our grouping symbol. A stretch, or in this case compress, because it's a multiplication, and because it's on the interior, we tend to do the opposite of what we would expect. In this example here, part G, I see a multiplication, so that's a stretch. Since it's on the exterior, we know that it's going to be a vertical stretch, so this is going to make it half as tall. That's pretty typical. The movement on the outside, or the indicator on the outside, performs just as we would expect. The adding of 2 means that it's going to be a translation or a slide of some sort. The addition means to slide. It's on the interior, so we know it's a horizontal move, and because it's on the interior, it's the opposite of what we would expect. So this graph is going to be half as tall as normal, and it's going to be 2 steps to the left. So let's see if we can recreate these images. Part A. One of the tricks that I had mentioned in the videos this week was to re-sketch the original graph and do so very lightly. So the original graph looks something like this. And if my transformation tells me to slide this down 2 units, then I'm going to recreate it where each of these data points, or the key data points, are all moved down 2 units. So I'm just looking at the y components, moving them down, and it looks to me like the end result is this position here. Now, there's a lot of extra ink on this, so I would like it if you were to erase your marks. If you want to leave your original sketch in place, that would be fine, although it should be drawn light enough that it could be easily erased, because the result that I'm looking for, the answer that I'm looking for, is the final position of your graph. And this one does indeed represent f of x minus 2. For f, I'm just going to place that here because we can see this. We know the graph is going to be half as wide. So what was originally this shape now gets reduced in width by half. So the x value that was here gets reduced in half. So what was a -2 becomes a -1. What was a +2 becomes a +1. This guy in the middle doesn't change. This x value of -1 becomes -1/2, and x value of +1 here becomes +1/2. And it looks to me like a drawing like this, whoops, would suffice. Let's get that straight line here. You'll be able to use an edge of a calculator or something like this if you want to create perfectly straight lines on your test. And there we have it. Our original graph was here, but the end result is here in blue, and that does represent f of 2x. All right, so that original one has been reduced from both of those. Again, this is what I'm looking for as a final answer, is your final shape when done. Now, part G, so that I'm not scrolling around, I'll just draw G right here. The original function was this shape. We should follow the order of operations when moving it. So I probably should have listed left 2 first, because we should work from the inside out. So we're going to shift our graph left 2 units, and if I'm considering my key data points, here's 1, here's 2, and here's 3. Each one of those gets shifted to the left 2 units, so here, here, and here. And this new graph, if just shifted to the left 2, might look something like this. But now if we make it half as tall as normal, each of the y values get cut in half, and the y value of 0 retains 0. The y value of -1 gets shifted to -1/2, and the y value here of -2 gets reduced to -1. So I'll erase that mark since it was drawn lightly, and I'll put in my final answer right here. Nice, clean, and neat, and we now have the equation y equals 1/2 x plus 2. So I think that collection of problems does a nice job of summarizing what I would ask on a no calculator portion of this particular test. I know I didn't complete all of the examples, but the timer on the screen showing about 25 minutes of discussion here. If you didn't have to talk and explain each of your work out loud, or each of your problems out loud, I would suspect that a well-prepared student should be able to finish this portion of the test in about a half an hour to 45 minutes time. In the next video, I will go over the calculator permitted portion of the test. Thanks for watching.